Hi, so let's pick up with reflections and guide reflections. This video will be a lot shorter than the last one because I realize now that I've covered some of the reflection stuff already in that last video. So just a reminder about doing reflections. If you have a reflecting line and you have a point that you would like to reflect over that reflecting line, so let's say this is point A. You're going to grab your protractor and you're going to line it up so that the reflecting line is at 90 degrees and that hole is right in the middle there. And then you're going to measure out. So whatever the distance is from the reflecting line to A, you're going to make the same distance from the reflecting line to A prime, and then mark it off. So now I'm saying that A and A prime are related to each other. In this case, the reflections across whatever line, and I'll call it line L for a reflecting line. Okay, the reflecting line is the perpendicular bisector of this line. So if you have the line that connects those 2 points, it turns out the reflecting line is actually the perpendicular bisector of the line that connects the 2 points. So give it a try, right? If you want to grab your protractor and measure this out, if you measure the distance between B and B prime, and you'll notice that half the distance goes from the reflecting line to B prime, half goes from the reflecting line to B. Try it with C. Okay, take your protractor, line it up so that it's on line M at 90 degrees. Whatever this distance is here, this distance will be there, and you'll roughly get a point that we'll call C prime right over there. Okay, and I put some directions down the bottom to kind of help you out. This thing you're going to have to print out and fold. It's a sort of nice introduction to reflections that doesn't get too technical if you're working with a younger group. Rather than pulling out protractors or dot paper, you can simply take this thing and fold it. My advice, fold it over line M, right? So make the crease go along line M, and then hold it up to a window or something and trace it on the other side so that when you open up the paper, you'll see that horse giraffe guy basically looking at himself, right? It'll be a mirror reflection, and the leg here that's closest to the reflecting line will be the closest leg on the other side. This one that's a little bit further will be a little bit further out, and then the head, as you can see, it gets progressively further from line M. He'll get progressively further from line M as he's looking at himself. So print that out, fold it over the crease right on line M, and then trace it over. If you have a nice sunny day, put it out by a window. All right, I'm going to suggest the same thing for this, except this time use a protractor. I mean, you can fold it over and trace it on the other side to see what it would look like, but then grab a protractor, set it up so that that line L is at 90 degrees on the protractor, and then measure it out point by point. You may want to extend this line a little bit to make it easier to see, but if you take B and reflect it roughly, you'll get B prime over here. If this is slanted this way, A prime will end up over here, and the figure should end up looking at itself. When you get done, it'll have the opposite orientation, right? Instead of going AB from left to right, it'll go A prime, B prime from right to left, but the figure will be exactly the same size, same shape. Whatever angle you have here at B, you'll have here at B prime. The lengths of the sides will be the same, right? If you measure it correctly, distance from A to B, distance from A prime, B prime will be the same. So that's one of the things that it preserves. All right, you can reflect things across an axis, right? Right over here is the y-axis. Can you reflect this thing over the y-axis? Sure, you don't even need a protractor. If you take -1, 3, right, that's point A, -1, 3, and you reflect it across the y-axis, the y-coordinate remains the same. It's the x-coordinate that changes, so it moves from -1 to +1. So this new point here is going to be +1, 3. So when you reflect it across the y-axis, it's the x-coordinate that changes. All right, instead of being 5 units to the right, it's going to end up being 5 units to the left. So if I moved over 1, 2, 3, 4, 5, point B, or in this case B prime, will be over there. Okay, and then C will also be on that same line, but further down. Instead of being at 5, -1, it'll be at -5, -1. So 1, 2, 3, 4, 5. If I drew this right, that should be your C prime. And then you can connect the dots. Right? From there to my point over there. And then connect the dots down there. Okay, so there's a reflection across the y-axis. So when you reflect across the y-axis, every xy point changes the sign of the first coordinate. So your xy's become negative xy's. If you reflect it across the x-axis, then it turns out that the y values change. So if you cross the x-axis here, instead of at 5, -1, it would be at 5, +1. All right, there's a little story about light reflecting from a surface. if you have a mirror or some other surface that light reflects across, the angle of incidence and the angle of reflection are the same. What that means is that this angle that it approaches the wall or the mirror on this side will be the same as the angle that it goes across on the other side. Now, the next slide actually has a video which would have been a great guest speaker. I'm going to post that video separately so that you can see it without having to click through the link on the PowerPoint. It has to do with the game of billiards, and actually, I'll blow the secret here. It's part of a video that was produced, I don't know, probably 40, 50 years ago called Donald Duck in Mathmagic Land. And Donald Duck is trying to shoot billiards, and he's using the idea that if you approach on this side, you'll be able to see where your shot goes by looking at the angle that it approaches and then the angle that it leaves. So if it approaches on this side and you look at the angle of reflection, it'll reflect across on the other side there, right? So the angle that it approaches over here is going to be the same as the angle that it leaves over there. And if you can sort of use the markings on the side of that table to help you guide those reflections, then you're not just kind of making a shot in the dark, you're actually looking to see where that goes. It's the same idea if a ball rolls against the wall and hits the wall, it's going to bounce out at that same angle. Okay, so I will post this separately so that you can see it. A glide reflection is a combination of a translation and then a reflection. And it doesn't matter what order you do it in. So take a look at this figure here, right? Here's A. I could take A, and the first thing I can do is I can do a vector translation and then a reflection. So the vector translation makes it look exactly the same, right? Same orientation and everything. Then when I do the reflection across this line, I end up with that figure C. That's the final answer there. I could have reflected it first, right? I could have reflected it first. I would have gotten a reflected figure up here and then done the translation and gotten exactly the same thing. So that's what a glide reflection is, right? You should be familiar with that term. A glide reflection is a combination of a glide and a reflection, right? So I'm going to do a translation and then I'm going to reflect, or I could reflect first and then do the translation. This I think I stole from your textbook. I kind of like it. Right, here's a car. That's my original one. There he goes. Now I've translated the image. When I translate the image, the car looks exactly the same. Now what happens? Now I'm going to do a little reflection. Oops. Now the car is upside down. Right, so I've done a glide reflection. I've taken my car, I've done a translation, and then a reflection. I could have reflected the car first, right? This guy would have ended up upside down to begin with, and then I could have moved him along underneath. Anything that I perform, isometry, whether it's a reflection, a rotation, a translation, glide reflection, all of those produce congruent figures. So this car that I started with here is exactly the same size and shape as the car that's here under the translation, is exactly the same size and shape as the car that's here under the reflection. So in this case, the glide reflection also preserves the properties that the original figure had, and therefore is congruent. So two figures under some kind of reflection, rotation, translation, glide reflection are congruent to each other. And that, in some ways, is how textbooks teach congruence, by performing these rotation, reflections, etc., and then saying, therefore, they are congruent. All right, that's the end of 13.2. Told you it would be shorter.